So week 5 and week 6 are still going on. So if you have any query in week 6, because I think week 5 is already covered in yesterday's session. So if you have any doubt in week 5, then you can ask. Otherwise, we will start from the week 6.
Sir, what is the difference between a heap and a binary search tree? I mean, when to use what?
Okay. So yeah, this is the topic from week 6. Okay. Any query from week 5? Okay, everything is clear in week 5. Okay, then I will take the week 6. Okay, so yeah, first question, what is the heap and what is binary search tree? What are the difference? So I think sir have already discussed the use of binary heap in. So basically, we binary heap have different property and binary search have different property. So what is the property for binary heap? So binary heap is also a binary tree, or it is we can say that it is complete binary tree. Okay, we will so if I am draw the tree, for example, like this is the first node. So like that. So binary heap basically is a binary tree and it is complete binary tree. If we start from the root, so every node should be filled from top to bottom and left to right in manner. Okay, so it cannot be like that. So if, for example, the shape for binary tree is like that, we cannot skip any node in between like that. So this is not present. So this is not a complete binary tree. Okay, so complete binary tree is that where every label should be filled from top to bottom, and uh, before the last node, all left nodes should be filled in the last label. For example, that this is the last label. So this is the last node in the last label. This is the last node at the lowest label. So all left side uh, positions should be filled. So this is called the complete binary tree basically. So but normal heap, this is the condition for normal heap, but we generally use the two types of heap. First is max heap and second is min heap. So what is the condition for max heap? So in this so in heap, every node should be greater than or equal to their childs. Okay, so for example, if we are talking about this root node, so this root node value should be greater than their child's node. So every node should be follow this property. So for example, so we can draw some example here. So for max heap, for example, this is 70, 50, 40, now then 20, 10, 30, 35, like that. So if you see the every node, so every node is value is greater than the value of child node. So 70 is greater than 50 and 40. So 50 is greater than 20 and 10. So 40 is greater than 30 and 35. So this heap this heap is called the max heap. And second version of the heap is min heap, where the parent node value is always less than or equal to the child's node value. So you can similar like that 10, 20, 30, 25, 40, 30, 32, like that is 50. In that manner.
So sir, in these there won't be any left or right property, right?
No, there is no property for left to right. There is only one property. Parents should be greater than or equal to the child's.
Okay, so we can switch 40 and 25 too.
Yeah, you can put anywhere. But in binary search tree, if you are talking about the binary search tree, so the property is for the left child and right child. So in binary search tree, generally we use the property like that. So for every node in this binary tree, left child should be less than to parent node and right child should be greater than to the parent node value. So this property should be followed by each every node in that. So this is the condition for binary search tree. So for example, we are starting. That. So 10, yeah, 5, 15, 12, 20, 1, 7. So if you see the tree, so every node, so 10, if you compare, so the what is the left child of 10 is 5. So 5 is less than 10 and 15 is greater than 10. Same for 3. So left child 1 is less than 3 and 7 is greater than 3. So right child is always greater than the parent and left child is always greater than, smaller than the parent node. So 12 is less than 15 and 20 is greater than 15. So this is the property for binary search tree. So binary search tree is basically used for the searching purpose. So we can search any value because element are arranged in sorted order. So we can search the element in login times. What's the height of the tree? Okay, so this height is called h. So we can search any element in login times. But you have already learned one method for searching binary search, where we are using storing the element in list. So what is the why we are using this binary search tree? Because in list there are some operation. For example, if we are storing the elements dynamically, so if we have a list, for example, this list have contain 100 elements, okay, and elements are arranged in the sorted order. So we can apply the binary search method and we can search the element in login times. But what happens if we want to insert any node in between, and if we want to delete any node, delete any value from the list? So what are the complexity for that operations? If we want to insert or any value in the sorted list, for example, if we have a list like that 1 of 3, 4 till 99, so 2 is missing, and I want to insert the 2 at that position 2. So every element after 2 will be shifted 1 position by index, because the previous list, this is the 0 index, this is the 1 index, but after inserting 2, the all index will be updated. So because of that, the complexity will be big O n in list. And if you want to delete any element from the list, it takes big O n times. So dynamically, when we are storing or deleting element dynamically in the sorted list, so if our elements are arranged in a list, so the insertion and deletion operation takes big O n times. But when we arrange our elements in the binary search tree forms, so we can perform these operations in log n times, insertion and deletion. We can insert the element in log n time, we can delete the element in log n times. So this is the benefits because of that we are using the binary search tree. we can perform search operation in log n time, we can perform insert operation in log n time, we can perform delete operation in log n time. So this is the benefits of binary search tree. Or binary heap. So binary heap, we basically, sir, give some example. We can use the binary heap in for the priority, for maintain the priority, or we can use this heap for I think sir explain you the use of heap in this Dijkstra algorithm to reduce the complexity. So because the creating the heap takes big O n times, yeah, I think I'll come with the slides. Just wait, I'm taking the slides. Six. So yeah, priority queue. Yeah. So one examples are given priority queue topic in week 6. So what happened when so this is the example: a job scheduler maintain a list of pending jobs with their priorities. So if we have a problem where we are maintaining a priority and we are executing the jobs according to the priority, so we have some algorithms to takes the less time to insert new jobs in the priority queue, and if we or I think should take less time to remove the highest priority jobs from the queue. Okay, so how we can solve this problem efficiently? So sir explain this one example job scheduler. So here when the processor is free, the scheduler picks out the jobs with the maximum priority in the list and schedule it. So there is one operation where we will remove the job which have the highest priority every time, and maybe some possibility some new jobs are coming continuously, so we have to insert this new job with some priority in our priority list. So this operation also should be performed in efficient manner. So how should the scheduler maintain the list of pending jobs and their priority? So there are two operations basically we require. Need to maintain a collection of items with priority to optimize the following operation: delete max and insert operation. So generally what we can, so compare some operations. Yeah, priority dimension structure. Insert. Yeah, so unsorted list insert operation takes big O one time, delete max is take big O n times. And if our list is sorted, so delete max takes one time, but insert operation takes big O n time. So this is the naive approach. We can reduce this complexity by taking a two-dimensional data structure. So here you can see that we can store the 25 jobs with their priority. So in we are storing the each job. So each row we are storing each row in increasing order. So for example, you can see the first row 3, 19, 23, 35, 58 like that. So when we insert new job, so we will check which row is empty, because we have already seen the first two row is have already filled. We will check the third row, and if our priority of the new job is for example 25, so we will store the new job priority at the fourth position. We will store our fourth priority here. Okay, so it will take the under root n time. So n is 25, so what is the square root of n? 25 is 5. So every time we want to perform an insert operation, we want to insert a new job in our priority data structure. So we will just check the I think one more thing is given. Yeah, this one. So we are maintaining one more list here. Actually, this list contains how many elements are stored in each row. So first row 5 already filled, second row 5 already filled, third is 3. So we can directly check from there and which row is empty now. Then we can insert the new jobs in that row with that complexity. Okay, so if we have a priority, so then for example, if we have a highest priority 35, so we will insert 35 here. Or if we have a lowest priority, then we can manage these things by sorting this element 10, 30. For example, new job have a priority 5, so we will shift the 5 here. We will store the 5 here and shifted the each node one position. So 10 will become here, 13 come here, and then 20. Okay, so in this data structure, so we know that the last column contain every time the largest value. So this last column contain the highest priority. So when we want to search the highest priority job, so I am talking about the delete max operation. So we have to search only this last column, max column. So 58, 67. Other is empty. So we will pick the highest value from here. So we will pick this one to perform the job. Okay, so we can insert the new element in under a square root of n times, and we can remove the delete max from square root of n times by this data structure. But it is also not efficient. So this is the insert operation takes square root of n times, scan size, and same for the delete max. Maximum in each row is the last element. So we know that in each row, last element is the maximum. So we will always check the last value of the each row. We can directly find out the maximum. So 58, 67, 20, 49, 14. So we will select the max value in these 5 values. So this operation can also reduce by square root of n. So this is the general priority queue, but we can maintain this priority queue operation using heap methods. So this is also an efficient method. So what is the next slide? Yeah. So this is the limitation of priority queue. We need to maintain a collection of items with priority queue to optimize. Yeah. So delete, there are 2 operations, delete max and insert. So how we can improve these operation time complexity? So we can use the heap binary tree. So now heap is introduced for this priority queue operations. So this is the first thing where binary tree is introduced. So binary tree is the tree data structure. Basically, it is a tree data structure. Binary means each node can contain maximum 2 childs, either 0, 1, and maximum 2 childs. So which node have the 0 children called the leaf node, and if any node contain the one children or 2 children called the internal nodes. So every nodes at the last position called the leaf node. This is leaf node, this last, these all are leaf node. And first node we generally call the root node, and remaining nodes we call the internal nodes. Sometimes we also call this leaf node as an external node. Okay, so terminology is also important for the tree and graph structure. So heap, heap. So this is the binary tree definition. So tree, basically what is the tree? So tree is a non-linear type of data structure which uh, where each elements are connected in hierarchical manners. So binary tree is the type of the tree, so where each node can contain maximum 2 childs. And heap is a binary tree where this binary tree is filled label by label and left to right. So we can say that this is complete binary tree. So the value of each node is at least as big the value of its children. Yes, we have already discussed these things. Max heap, min heap. So yeah, no blank space allowed in between. Okay. So this is the not perfect heap. This is the perfect heap. Insert operation, delete operation, sum operation. So yeah, some algorithm are there. So what is the complexity of build max heap? So we can create a max heap in big O n times. We can perform the insert operation in max heap in log n times. We can perform the delete operation in log n times. So
Sir,
these are, yeah.
sir, the approach sir discussed about for making a heap in order in time. Can you like elaborate on that?
Okay, how can we create a max heap in log n time? No?
In order in.
Order in.
Originally, it was a L log n when we were taking every element from the list and like placing it at the right place. But then he told something about like slicing the list from the middle part and like those will be the leaf nodes. And we can create an order in time. That part I didn't understand.
Okay.
The better EPY method, right?
Yeah, the better heapify.
Heapify. Okay. So generally, actually, we know that this is the complete vanity. So we can implement this using the list. Okay. So for example, this is the so heapify method takes log n times. Okay. Build max heap, I think. Max heap is okay. I'm confused. Build max heap. Insert. Complexity of insert first time. Okay, so I'm just starting from here. For example, we have a list. Where I want to 1, 3, 6, 7. We want to create a max build heap. Max heap. So okay. So we will start from the first nodes. We will insert as a node. So this is the one. After that, second we will insert at here. So 3. Then I will apply the heapify method on every time. So sorry, I have to use the build max heap method. 3. 1, 3. Okay. Actually, we can create it directly a directory. Okay, directly like that. So we are starting 4, then 2, then 8. Then
Yes,
6.
creating the heap, then we will check that it is
Yes.
heap or not.
Okay. So we will create the tree. After that, we will start from. So what is the index of each node? This is the 0 index. This is the 1. This is 2. This is 3. This is 4. This is 5. This is 6. Actually, our elements are stored in the list, but we are representing as a tree, where we can find out what is the. There are some formula. By this formula, we can calculate their childs or parents. So what is the formula is that? So we can calculate hi. For example, what is the left child of who is the left child of hi? So formula is 2 into I plus 1. Okay. Right child formula is hi2 into I plus 2. And what is the parent of I? So this is basically
I minus 1 integer
Integer.
division
I
into
minus 1, 2. Correct? So we can identify the parents or childs by these three formulas. So how can we make this as a max heap? So this operation we are consider that this is a heap. So we will apply the heapify method from the n by 2 nodes. N by 2 nodes. So what is the 1 second, n by 2? Yeah, so 0, 1, 2, 3, 4, 5, 6. Yeah, no. I think n minus 1 by 2. Yeah. Oh, 5 minus 1, 4 by 2. No, no. Yeah, n by 2 minus 1. This is the formula, I think. So yeah, we will start from that node. Yeah, that means we will start from this node and make this part as a max heap.
Sir, can you like elaborate on why we start from the middle of the list, like n by 2?
No, so actually, how we can create a max heap? So these are three elements. So what is the property of max heap? So in every subtree, every combination of parent or child, okay. So the maximum element should be come at the top as a parent.
Yeah.
Okay, so if you for example, if you start from there, so it is also a max heap because single element is already a max. We can say that this is a max heap. If there is only single elements, so we can say that this is a max heap because there is no child. So why we can why there is a need to apply the heapify method on these leaf nodes?
And if we heapify their parents, then the child will itself be heapified, right?
Yeah, so we will start from the parent node, first parent node. So this is the first parent node from the bottom, okay. So we will start from here. So we will apply the heapify method on this part. So we will find out the who is the largest on these three elements.
So
Okay.
from 4, we will check that if its left child or right child is bigger than it. If it is, then
No,
we
so
will swap
there
it.
is a simple step. We can follow these steps. So we will just check the largest equal to I. For example, this is the I. So I is equal to 2. Okay, this is index because we are performing the operation on list. Actually, we are performing the all operation on the list, but we can understand by this tree representation. So we will start from that. We are assuming that largest equal to I. After that, we will compare this largest element. If largest, for example, for example, our list name is A. So A largest is less than the right of. Okay, so what is the formula for right? We will calculate the right for value from this formula. So what is the I value is 2. Okay, so we can okay, I'm calculating. Yeah, I'm comparing from the left child. So what is the formula for left child is this. So I is 2, then 2 into 2, 4 plus 1, 5. So we will compare this element by fifth element. So A, I'm just writing that the left child. Okay, if A largest is smaller than A left, so what will be the largest? We will say that largest equal to left.
Left.
Okay, after that we will compare that this largest to right child. So if A largest is less than A
Yeah.
right. Okay, so we will shift once again, we shift largest equal to right. So finally we will get the index of the largest element. Clear?
Yeah, but we would have to swap too, right? Because
Yeah, we have to swap, but we will swap after
after
finding the largest
comparison.
value. Yeah. So
Yeah.
after that we will check if largest does not equal to I. Okay, this position. If largest does not equal to I, then we will swap the elements. So A I to A largest. Got it?
And
Yeah, and
recursively heapify the large from the largest node.
Yeah. So we can understand by this tree. So we are starting from this node. So we are considering that the 2 is the largest, and then we will compare the element 4 and 6. So who is the next largest is 6. So largest index equal to 5. Then we will compare then 6 and 7 value. So what is the largest value is now 6. This index 6. Okay. So finally we will get the largest index is 6. So we will check largest is not equal to I. So initially the I value is 2. So I value is 2 and the largest value is 6. So largest does not equal to I. So we will swap these two values. So 7 come here at the 4th position. 7 come here and 4 come here. So this part have already become a max heap.
so it's like exactly half of my nodes would be leaf.
I think there is one property we can say that not half n plus 1. I think no, we cannot say that. Yeah, if we have a complete, for example, if we can note at 1 here, so 1 2 3 4. What is the internal nodes? 1 2 3 4. So exactly we cannot say that, because in that case there are 4 but internal are 3.
So, sir, if we can't exactly say that, and when we run heapify from the middle of the list, then won't there be discrepancies in?
No, so for example, if we are adding one node more, so what is the index is 7. So 7 divided by 2. So 7 divided by 2. Okay, so what is the value?
That will give 3, right?
3. Yeah, 3 come here. So what? 0
A minus 1.
3 minus 1, no. But parent of this node is this one. 3 pa. 1 2 3. So value is correct 3. So I think we can take a common formula. No, 6 4 3 4 5 6 6 divided by 12.
So we are starting from 0. So total length is 8, right? So 8 by 2 minus 1.
Oh, there is one formula actually given. I think in slides there is one formula given. Delete max, CP5. Implementation. This is parent information. Better heapify. Yeah, so mid of length of, okay, we will divide by the length of 2. This is the formula, length of 2.
Yes, sir. So here the sir is saying like from the middle of the list will start. So does it mean like exactly middle, like exactly half of my elements would already be leaf?
No, what are you saying exactly? So for example, what is the length of this node is till now is 1 2 3 4 5 6 7. So 7
Length of,
divided by
what?
length of the tree, or we can say that the length of the heap.
3, right?
Is there any one? Sorry, 0 1 2 3 4 6. So total elements are 7.
Half of the elements are leaves here, right? And it will always be in every case, right? You can see, you can draw every possible heap.
No, so For example, if we have a tree like that. Yeah. For example, we have a tree. So there are 7 elements here. So actually, we will start from this node. UPPy method, we will start from this node. So how we can get this value? 0, 1, 2, 3, 4, 5, 6. So 7 divided by 2 minus, okay, got it, minus 1. We can say that 7 slash 2 minus 1. So we will get the 3 minus 1, 2. For example, if we take one more element, this is the 7. So now element become, so element become 8. 8 slash 2 equal to 4. 4 minus 1, 3. Yeah, 3 is the parent. So we will start from here. Yeah, so this is the formula basically for starting the HippyPy method.
Sir, that is
The
clear.
length,
But
length of,
you can see still after adding the edge, still we have 4 leaves here, which is half of the total nodes.
okay, so for example, if we create one node more, so now this time is a half or not?
Yes, sir, it is there are 5 leaves and total 9
Yeah.
nodes.
Yeah, so this is not the half, no?
But it is more than half,
Yeah.
not less than half. It will be
So
always.
I think this formula will work.
Yeah.
Len of a flow division by 2 minus 1. We will start the HippyPy method from this position.
Yes, sir.
Okay.
This formula will work always. Actually, I
Yeah.
tried coding this.
Yes.
Sir, this means we have to add the next node in this position. That's what you're saying, right?
Next node? No, we are not adding any nodes.
Okay.
We are performing the HippyPy method. Actually, we have a one tree. We want to convert that heap. So we can say that we have a one heap. We want to convert that heap into a max heap. So we will apply the HippyPy method from this position. This position. Okay, just once again I've created some confusion is there.
Yeah,
So,
yeah, I get it, sir. Yeah.
okay.
Yeah.
So yeah, in the previous example, yeah. So after HippyPy this process, so it become like that one. Create again. So 1, 3, 1, 3, 7. What is this? 2, 8, and 6, 4. Okay. 2, 8, and 6, 4. 2, 8, and 6, then 4. Okay, we have already applied the HippyPy method on that. Now we will move to the next part. So this is the 2 index, this is 1, this is 0. 0, 2, 3, 4, 5, 6. So we will start from the apply the HippyPy method from 2 to 0. Okay, one by one. So we have already completed this. Now we will apply the HippyPy method on that first position. So HippyPy method convert this part into a max heap. So after that we will get the 1. So 8 will swap by this 3. So okay, so 8, then 7, then 2, then 3, then 6, then 4. Okay, so after that we will apply the HippyPy method on that part. So who is the largest? 8. So 8 will swap to the 1. So 8, then 1, 7, 2, then 3, 6, then 4. But after apply the HippyPy method, we always check that the child node. We always apply the heapify method on the child node, because when we, for example, this, so after swapping this 1 and 8, so now it become it violated the max heap property. So we will apply heapify method on this part again. So after this part, so 8, then this will swap by this 3, and 7, 2, 3, sorry, 1, and 6, and 4. So this is the max heap now. So we have to perform this n by 2 operation basically.
So theory wise I get it, but algorithmically I'm not able to get it how we would go about like even writing the pseudocode about this.
So you are not able to write a code for this.
Like I'm not able to think how to write a code for this, because like we are going visiting, like when we swap 8 with 3 and then that is the root node, it is the root node, then we have to come to one like on the previous position of 8 again and then do the swapping again.
So actually there is one recursive call inside the heapify methods. So currently I have no method for heapify, but we can try to write the code. Okay. If anybody have the code, you can share. I think.
Yes, sir. I have the code. I can share the code.
Yeah, because it will take some time. Yeah. I think some problem have some problem basically heapify method inside any problem. I check it. Assignments. Max heapify. Yeah, this one. Can you see this code?
Yeah.
Yeah. So I'm taking a picture. 1 second. Yeah. So this is the heapify code for. So here we are. This is the algorithm. This is the algorithm for create a build max heap. So we are starting from this formula. Okay. For k in range n to -1. So this -1 is the last index. It will not come in the range. So this loop will be k will be moved to n to 0. Okay. And we are applying the max heapify a comma k. So where a is the list. Okay. So here we are calculating the left child value and right child value. This part, left child value by the formula and right child value by the formula. Okay, we are starting from this k position, because we are passing n value as. So after that, this is the recursive call, max heapify. We always apply the heapify method again if we swap the value. For example, we are performing this. So for example, this is 1, this is 2, this is 3. Okay. So we know that when we apply the heapify method on that, so this one value will be swapped by this 3 position. So finally we will get that this is the I, or finally we will get the largest position, largest. So after swapping, we will apply the heapify method on this largest position again, because after swapping, it can violate the property of the lower part. So after swapping, this 3 come up and 2, then 1. So we will apply the heapify method on this part again to maintain the max heap property on the lower part. Okay,
Yeah,
so
got
this
it.
is okay. So this is the recursive call. We will apply on the k position. Largest equal to k. I think this something is. So yeah, we are applying the k. So k is the initial largest equal to k. So, okay, okay. So I think something is wrong. We will apply the max CPY on a comma largest.
The third if condition is also wrong. Not equals to k, I guess. Largest will not.
So I think question is related about this wrong condition. Oh, okay. Yeah, we are asking the what is the wrong condition. Incorrect implementation. Okay.
Yeah. Line 9, 9, 11.
This is graded question. Okay. Yeah. So I've only told that this is not a correct value. This should become the largest. So after swapping, if we are swapping this with this one, for example, like that 1, 4, 3. So after swapping, so after heapify method, this is the I value or this is the largest value finally. Okay. So after swapping, we will perform max heapify on this node again, on the lower part. So it will convert the lower part max heap again if it become a wrong.
Yeah, and it will keep going like until the leaf node, and then everything would be.
So you can write the heap max heapify code using this. I think there is only one or two change. You can write the code. Okay. So this is the max heap part. Anything others?
Sir, in max heap only, can you explain how we are applying this to Dijkstra?
Okay, that's the. So we have to come up back again. Using heap in legal algorithms. In Dijkstra algorithm, we are actually using the min heap, I think.
Yeah.
Because every time we need to find the
Minimum
nodes
distance.
which have contain the minimum distance. Yeah. So this is the old algorithms. So we are using this condition. Okay, next d equal to min. So because of this condition, we have to visit all the nodes and check to that which contains the minimum distance and which is also not visited. So it takes order of n times. Finding the minimum distance node takes the n times. Or same things for the next line. I think next we list. Not list. No, not this line. I think yeah, this one. Min. No. Okay. So actually, we are improving this part. Next equal to finding the minimum distance node, which are not visited. Because we know that after creating a min heap, we can remove the node minimum value in login times. Okay, so we are improving this part. Delete min in login times. Generally, our naive approach taking the complexity is big O n part, but using this min heap, we can improve this part into the login times. So updated implementation is not given, I think. So actually, I think sir maintaining the another list for that. Yeah, this one. So yeah, I think this topic is theoretically discussed. Actually, we are maintaining a dictionary. There is one maintaining 2 additional dictionary. Okay. One for V2H, second for H2V. So what is V2H?
It map vertices to heap index.
So V2H, this dictionary contains the maps vertices to heap position. Okay, so 0. What 0? Vertices. Okay, this line contain the vertices number, and where is that node inside the heap? This is the heap position. Okay, so this is 0 vertices at the 7th position. Okay, number node not again 0 1 2 3 4 5 6 7 8. Okay. So first dictionary contain the vertices node position inside the heap. So this 0 node at the 7th position, 1 node at the 3rd position, this one. And second dictionary we are maintaining H to V. We are heap position into vertices. Okay, this is the reverse things. So 0. Okay. At 0 position we are storing the 7th vertex. This is the vertex now, and this is the heap position. I think theoretically it is difficult to explain.
Sir, here our heap would be like a list of lists.
Actually, we are maintaining inside the dictionary heap.
Inside the dictionary?
Yeah, actually, we are maintaining 2 dictionary. Na? So, vertices are 0 to 9. These are dictionary actually. V2H and H2V. These both are dictionary.
We are storing tuples inside the list path because we need both vertices and their weights.
So, but actual implementation is not given, I think. So, this is because. Okay. Okay, so I think theoretically it is difficult to explain also. I will write the code for that and I will post it on the site. Complete code after implementing this part. But we are improving this actually only by this position. We are improving this part. Because finding the minimum distance node which is not visited takes the big O n time in our matrix, because we have the weighted matrix. It takes the big O n times, but you know that in min heap we can remove the minimum value in log n times. We are improving only this part.
The second loop also we are improving our.
Actually, we are after selecting, we are updating the all distance, all the weights, all the adjacent weights. You can say.
Like finding.
So we are updating the weight. Yeah, we are updating here.
In nested loop, yes, sir.
Yeah. So we are updating the weights from here. So we can improve this part as well.
So like how much would that improve, like login or
min distance of v equal to min distance of v distance of next v plus the min part. So matrix if w matrix equal to 0 not visited. What also need to update distance of neighbors. Unvisited neighbors distance are inside the min heap. Inside the min heap. Update the value is not a basic heap operation. Distance of V. So neighbor distance in matrix, we want to update the matrix. Close part. Change value, okay. I think we can discuss after the implementation the new code. Because
Okay, sir. And sir, if
implementation
possible,
is-
can you alongside the code, can you write a short pseudocode too, so that like if we don't want to see the
because
code,
I have to create the pseudocode also.
no,
Because
like
here
you can
the
just write
logic
in
is
English, like if you want.
yeah. So sir, I have already given some hints for
No,
this.
like after on the website when you are doing
Yeah,
that
yeah,
part.
sure, sure. Okay. Yes, I'm also creating a notes. Our notes are not completed till now. I will upload all the implementation. I think I know that week 6 the implementation part is less. Kruskal algorithm, I think using union finds is also not given. So
I've
I
actually
will
done the Kruskal part. If you want, like I can send you
Yeah,
using
union find.
you have already done.
Yeah,
yes, sir.
I think it works, but not sure.
Oh, you have already checked or not?
I have checked. It is giving the MCST, but I don't know whether time complexity if it is.
Okay, okay. So I think I have given one link on the website, so you can share
Okay, sure.
your code, and not website on. I have shared the
On the
link on
Google Form link.
Discourse. Discourse, yeah, Google Form link. Yeah, you can share your code at that. So I'll check. Otherwise, I am already working on that. After creating the code, we will discuss on that. Okay, so without coding, I think it is difficult to explain. Okay, any another topics? Yeah, yesterday Dijkstra said some students have the difficulty to understand the Kruskal algorithms. Binary search, I think it is clear to all. Delete operation. So delete operation in the binary search tree. So I'm just revise the operation of binary search tree. So main part of the week 6 is binary search tree or heap actually. So in the binary search tree, for example, if we have a sequence, can you tell me what is the maximum height for the binary search tree if n equal to, for example, 10?
And
Okay. So what is the condition?
to simply join all the nodes in a straight line.
Okay, good. So yeah, for example, if we are creating binary search using this sequence for 1, 2, 3, 4, 5. Okay, we are creating a binary search tree using this sequence. So what type of the binary search tree will be created? So we will start the adding 1 in the empty binary search tree. After that, when we insert the 2 node at the binary search tree, so we will every time we will compare the new element from the root node. So 2, we will compare the 2 from the root node. So 2 is greater than 1. So yeah, empty place is available at the right side of 1. So we will insert at the 2 here. Now we will check 3 again. So we will start comparing 3 from the root node again. So 3 is greater than 1. We will move to the right. Okay, 1 node is available. So 3 is greater than 2. Then empty place is available. Now we will add that 3. Okay, same for the 4. 4 is greater than 1, then greater than 2, then greater than 3. So 4 will be insert here. Same for the 5. So at this situation, the height is equal to 1, 2, 3, 4, and 5. So n equal to 5, then h is also equal to 5. So this type of property question sometimes asked in the papers. So what is the if n equal to 5, what is the maximum height over, so, and what is the minimum height? So can you tell me, if n equal to 5, then what is the maximum height or what is the minimum height? So maximum is 5. What is the minimum height?
3. Yes.
3. Yeah. So if binary search tree is created in the complete binary tree form, so for example, if we have a sequence like this, 3, so okay, 3, 2, 1, 4, 5, like that. Okay. So I'm not sure what is this tree will be created. So we will start from the 3, then 2, then 1, then 4, then 5. So height is equal to 1, 2, 3. Okay. So yeah, this is the binary search tree. So this type of question asked in the exam. So sometimes height is given. So for example, height is given h equal to 10. What is the minimum number of nodes and what are the maximum number of nodes? I'm just taking a small value. For example, 4. So what are the minimum number of nodes and what are the maximum number of nodes in the binary search tree? This is a reverse question. Initially, I am talking about the n is given and I am talking about the height. Now I am given the height. Now what I'm talking about the number of nodes. So h equal to 4. What is the minimum number of nodes and what are the maximum number of nodes?
Sir, I think minimum number of nodes should be 4 and the maximum should be 2 to the power 4 minus 1. Right?
Yeah, correct. So this is the minimum. So when a tree is created in that form, so this is the minimum situation. And maximum is 2 to the power 4 minus 1. That is called 15. When our tree is created in complete binary form like that.
So if you're given like the number of nodes, n is equal to 5, and we have to tell what can be the maximum height, the minimum height of the tree, we can just take log base 2 of that n, and that would give us, right?
Yes, yes. So we, if number of nodes given, so minimum number of height can be given by log n formula. Log n, or we just add one element here. This element come here. So log n plus 1, like that. So this is some properties related to the binary tree or binary search tree sometimes asked. So sometimes ask the questions, if number of nodes are 10, what are the minimum number of edges? What are the number of edges in binary tree? So always edge in the binary tree is 1 less than nodes. So 9. So edge are given. So number of nodes sometimes asked. So if given that in the tree, if 9 edges are available, so how many number of nodes are there? So we can add by 1 equal to 10. So some relation, some property is already available with the binary search tree, binary tree. You can explore these things. So otherwise, operation, I've already tell the how the insert operation perform. So same for the searching operation, find operation. I have a code for that. 1 second. Yeah. Your code is visible or not?
Yes, sir.
Yeah. Okay. So these are some operation. So this is the in order. Yeah, there are three type of traversal generally we used in the tree traversals. First is in order traversal, second is pre-order traversal, and third is the post-order traversal. So do you know about these pre-order and post-order terms?
Yes, sir.
In order, I think already given in the B6 codes. I think pre-order and post-order are not given. Yeah, some question I think related to this in order and pre-order in the graded assignments.
Sir, when do we use these, like in while writing codes or like in competitive programming? Because like these are like such long codes. How can we even implement binary search trees when we have like time constraints?
So these are some concept actually. This so what concept can be used in which problems? It depends on the problem. So this is the long code, but there are many operations inside. So sometimes, for example, if you want to just apply the searching part, so you have to retain only this part on the binary search tree. For example, some tree is given, and you ask there in question in you are asking that find the element in login time. So you have to retain only this part, not the complete part.
Okay.
Okay, same for the you sometimes ask the what is the maximum element, what is the minimum elements in the tree. In the binary search trees, you have to retain just a small this 4-line code. Not this is the complete implementation actually. There are many operations given inside. Delete, make empty, copy left, copy right, this part. So for the delete, I think delete operations some are tricky operation in binary search tree. What is the concept for delete operation? To discuss. So for example, if we have a tree, what are the situation for the delete operation? So for example, this is 30, 15, 10, 20, 40, 35, 60, for example, 32. Okay, this is the correct. Yeah. So we can delete any node, but how we can perform the delete operation? Because for example, if we want to perform a delete operation, so there are three type of situation when we perform the delete operation. So first case is when, for example, we are deleting the node B, and first case is that if we node have no childs. Okay, so first case is there is no child, 0 child. Second case is if deleted node have only one child, and third case is if deleted node have two childs. Okay, so these three type of case can come when we are deleting the node. So for example, if we are asking that remove the node 32. Okay, so 32 have 0 child. We can directly remove by the removing the link on the parent node. So at this position, we can directly put the left child field in, so we can directly put none in left child of the fields in 35. Okay, so this will be removed directly. Okay, so second thing, what happened if we want to remove the node which have the one child? For example, we want to remove this 35 nodes. So we can directly perform this operation. We will just find out the parent, who's the parent of 35. 35 parent is 40. We will put the address of this left child. Okay, so we will put the address of 32 inside the here. So the 32 will come at the 35 position, and then 35 will be removed. So this is the second case. It is also easy, but what happened when there are two child available of the deleted node? So for example, we want to remove this 30. So how can we remove this part? So generally we use a two approach. So we can swap these 30 30 nodes, or we can say that we want to remove that node which have the 2 childs. We can swap the value of that node by the in order successor, or we can replace swapping this value by the in order predecessor nodes. So what are the in order successor? What is the in order predecessor? So in order traversal, if we traverse these tree, so what will be the order? So 10, 15, 20, 30, and 40, 35. Sorry,
32.
32, 32, 35, 40, then 60. This is the in order traversal. If we want to remove this 30, so we can swap the value of this 30 by in order successor. So in order successor is this 32. In order predecessor is 20. Okay, we can swap the value by anyone. So for example, we are performing the swapping operation with a successor. So 30, we will swap the value is 30 by this 32. This 32 is the successor of 30. So after swapping, this become a 32, and this is become a 30. After swapping, we can directly remove by this, either using this zero child methods. We can remove directly this node. So we can perform this operation for removing the node which have the 2 childs, or we can perform the another part. We can swap the element by in order predecessor. We can swap this 20 to 30. So after swapping, this tree become like that: 20, 15, 10, and 40, 35, 60, and 32. Yeah. So after swapping, we will remove this 30 from here. So this type of deletion, after this deletion, our tree will remain the binary search tree. So these 3 cases you have to maintain in your delete operation. So this is the theoretical part. You can implement this delete operation using 3 cases. You have to handle this 3 cases in your delete operation.
Sir, is there like how can we recover this linked tree from the list?
Sorry, I'm not getting your question. How can you recover
This linked tree from the list? Like you are removing the element by converting this into list.
So after removing, how you can recover? You cannot recover because you have already lost the address of node. If you are storing the deleted node address in anywhere, so you can recover. Otherwise, you cannot recover.
No, sir, not the node. I am asking about the tree, complete tree.
So recover.
Like if we have a tree in the form of in order list, like in order traversal form of list, then how can we recover?
Oh, okay, I got it. Okay. So you are asking that if in order traversal is given, or pre-order traversal is given, post-order traversal is given, so how you can create a tree?
Yeah, algorithmically, practically.
Yeah. Practically. Theoretically you got?
Theoretically, I got it, sir.
So theoretically you can create a code for that. So practically, I think I did not create any code. But I think in binary search tree, it is easy, I think. Maybe some. So in pre-order, for example, in order, I think this is difficult. In order, you cannot create because you don't know who is the root node. But in pre-order, you know that always the first node is the root. Yeah. And post-order traversal, you know that the last node is always the root. You can traverse from the back side. Okay.
And
so for example,
left right value, we can create the tree from there.
Yeah, simply. So for example, one tree is there. So I'm creating a small example. So 5, then 1, then 7, and 20, then 15, then 30. Okay. So what is the pre-order traversal? Can you write the pre-order?
Yes, sir. 157. No,
Okay.
it's in order.
The pre-order traversal start from the, actually we can use a small formula. So in order traversal, we follow the recursive algorithm like that, left, print, and right. So for example, LPR. So L means we will move to the left part, R means we will move to the right part, or P means print the node. Okay, so same for the pre-order traversal, we can perform formula PLR. Okay, we apply this recursive formula on the root from the root nodes. So PLR.
10, 5, 20.
So first step will be executed, not 10 will be printed. Okay, now
And-
second step is L. So we will move to the left part. So once again we apply the all three steps PLR. So first step will be executed, then 5 will be printed, then once again left, PLR, first, yeah, then 1. There's no left, there's no right. After completion this step, we will move back the recursive call. So L is completed. Now we will move to the R part. Okay, so R is P L R. So first step is P, 7 will be printed. Now left is, there's no left, there's no right. Completed. Now R part is complete. Then move to back to the 10. Then move to the right part now. Okay, so right is this P L R. So this is the P part. So 20 will be printed. Then we will move to the L part, left part. So PLR, this is the 15. Okay, so no left, no right, then move to the parent, then move to the right part, PLR. So this is the print part 30. So this is the pre-order traversal, okay, for the given tree. So if you have a pre-order for the binary search tree, you can create a binary search tree. So you know that in the pre-order traversal, always first node is the root node. So you can create once again. So you can just create the binary search tree using this order. So 5 is come here. So next node is the 5. So 5 will link on the left side. Then next is the 1. So 1 is less than 10, less than 5. Then come here. Then move to next is 7. So 7 is less than 10, greater than 5. So come here. 20 greater than 10, 20. Now 15 greater than 10, less than 20. Come on the left, 20. So now 30 is greater than 10, greater than 20. 30.
We can basically
Okay.
treat it like a list and incrementally like build like a heap.
Yeah, we are creating the binary search tree using given sequence.
Yeah.
So using pre-order and using post-order, you can create. But in order, pre-order, and post-order, this type of question I ask with the normal binary tree also. I think this topic is not in your course, but sometimes you can see that with normal binary tree, for example, A, B, C, D, E, F, D. So I'm not saying that this is the binary search. So you can find out the traversal order for this binary tree also. So in order is, what is the in order? D,
B, E, A,
D, B, E, A,
F, C, D.
F, C, D. And what is the pre-order?
A, B, D, E, C, F, D.
Yeah. So we will start from the A, then B, then D, then E, then move to C, then F, then D. Okay. Now what is the post order? So what is the post order? We will start from, so formula for the post order is L, R, P. Okay. So move to the left, move to the left. Then there's no left, there's no right, then print D. Okay, then we will move to the B and then move to the E. So E will be printed, then B will print. Okay, then move to the A, then C, then F. F will be printed, then D will be printed, then C, then A. Yeah. So sometimes person, this is the normal things where you can find out the order, okay, from the tree. Sometimes question is asked, sometimes order is given, but you cannot create a binary tree using only one order. I'm not talking about the binary search tree here. So for example, if this order is given, pre-order, you cannot create a binary tree. What is the actual binary tree? So in this type, so always two combination of order is given, then you can create a tree. So this is also the important question asked in the competition exams. So for example, in order and pre-order is given, you can create a tree. If in order and post order both are given, you can create a tree. Same for the if pre-order and post order is given, then you can create it.
Sir, can you again explain the in order, how it is created?
If in order and pre-order is given, you can create a tree. How? So okay, we will start. So we know that if I am assuming that this two part is given. Okay, so we know that in the pre-order, first node is a root node. We can create a root node here. Okay, after that we are scanning from here. Okay, but we will check that what is the position of A inside the in order. This is the position, and what are the nodes available on the left side. So all nodes we will write on the left side, D, B, E. Okay, what are the right side nodes? So we can create F, C, D. Okay, so after creating this part, we will move to the next node of the pre-order. So the next node is B. Okay, we will mark as a node of the left child of A here. Now we will check that, we can directly check that on our this part. Okay, so what are the left of B, what are the right of B? So left of B is D and right of B is E. Okay, so after that next node is D, so we will mark as a D. Next node is E, we will mark as E. Now next node is C, so we will mark C here. And what are the left of C in this part? F. And what are the right of this part? D. Okay, now we'll move to the, so we have already marked the C, now F, now D. So once again we can create a tree. Okay, so this question sometimes asked in the competition, so you can explore these questions also. So in order, pre-order you can create, in order and post order given. So only difference is that if in order and post order is given, so you have to scan from this, from the right side. In the previous example, we are scanning from the left side in the pre-order, but in if in order and post order is given, then we will scan the post order from the back side one by one and create the same tree. But yeah, pre-order and post order is given, then some tricky operation is there. So sometimes some another forms is also created. So this is some extra things which is not, but you should explore all these things. But in binary search tree, we can create from the binary search tree using the order, because we know that. So what is the left? We know that the left child is always less than and right child is always greater than. So we can put the nodes according to that. Because of that, we can create a tree using pre-order and post-order, but we cannot create using in order. We cannot create a binary search tree using in order traversal.
Sir, but we know the root node in the in-order traversal, then can we create the binary tree?
If you know the root node of in-order traversal, so how you can know?
If it is given in the question.
Okay, so I think if root node is given, then the order, I think, it will, 1 second. Still, I think it is not, because you don't know the what is the left child and what is the right child.
Okay.
Again, so you can create the just for example in the previous question. Yeah. So what is the in order traversal? This is the pre-order. Okay, for example, this is given so 1 5 157 157 and next is 10 15 20 30 10 15 20 30. Yeah, if this order is given, so for example, if we are telling that what is the 10 is the root, so 10 is the root. Okay, so what order you will follow to fill the node now?
Sir, on both the left and right sides, we have three elements that will represent L, P, R.
Yeah, so what order you should follow to insert these nodes in given root for the given root?
And sir,
So
we
if,
know
for example, if you fill the order like this one, so this one become here now.
Can I put center of the left?
Sorry.
Center 157 is 3 elements, so I will take center of them.
yeah, central element is second, like child of 10.
Okay, so
Five.
what happened? Okay, so okay, 1 second. You are
We
putting
work
the
in
center
complete
elements. Okay, but what happened? For example, if node is given like that 5 2 and 1, okay, and 15
Yes,
20.
I got the point. This will only work in complete way.
Yeah, so order is that 1 2 5 10 15 20 and sorry 30 30, and this is the root node. Then this become clear. Okay.
Yes, sir, it's clear now.
Yeah, so using in order you cannot create the exact things. Okay, so okay, any other topic from the week 6 or week 5 also, or what about the quiz? Is there any doubt in any questions of the quiz? How was the quiz? No response for the quiz. Okay.
So I think someone in the chat wants to, like Samit.
Some correctness of classical and claims. Please discuss. Oh, correction part, correctness. Can you please explain Floyd-Warshall algorithm with the test graph provided in lecture? Floyd-Warshall, okay. Correctness of classical and claims. Please discuss. Okay. So yeah, one question related to Floyd-Warshall is also from the Anushka. So Floyd-Warshall. Floyd-Warshall, I will take one example. PDSA. Okay, graph is very big. make file. So for all pair shortest path. Yeah. So Floyd-Warshall actually the algorithm for the all pair shortest path. Finally, we will get the matrix where we can find out the all pair shortest path by the combination of row index and column index. So how it works actually manually, there are lots of value you have to calculate to solve. So 0, for example, this is the 1. So okay. So what is actually logic? There is one formula for the Floyd-Warshall algorithms. Okay, I'm just want this one. Yeah. 0, 1, 2, 3, 4, 5, 6, 7. Total 8 number of nodes are available. So you have to so initial what are the initial list is SP0. Okay, this is the initial list. So where the all value are filled according to this index row index to column index forms. So 0 to 0, generally for same index we fill the infinite, or if there is no edge we fill the infinite. Okay, so 0 to 0 is no edge, so infinite is there. 0 to 1 is edge, so 0 to 1, yes, this is edge is given. So first matrix is filled by this graph. Okay, directly. If there is an edge, we will fill the value of the edge width. Otherwise, we will fill the infinite. So after this first matrix, you have to create. So how many matrix you have to create? So there are 8 nodes. So you have to create 8 matrix like that. So first matrix is this. So how many calculation you have to do it? Yeah. So SP0 is the initial matrix. After that, we have to create SP1. Okay. So this is the second matrix where you will apply the formula. What is the formula? There is one formula, I think in my notes is given. The formula is SP K of I comma J comma K equal to min. So just check the formula inside. Yeah, this is the formula. SPK I comma J so yeah, IJ. So this K is these things given here. Min SP, yeah, SP K minus 1 I comma J comma SP K minus 1 I comma K plus SP K minus 1 K comma J. This is the formula. It's going to be used. Yeah. So for next matrix, we apply this formula. Actually, this 0. So this 0 is represent that 1. I think sir used some different things. So you have to fill every single value of the matrix using this formula. So for example, this is SP0. You have to fill this next SP1, this value. So what is the index for this? So I equal to 0 and j equal to 0. And what is the value of k? K equal to 1. Okay. K, so I equal to, yeah. So you have to apply this formula. So you will check the value from the previous matrix always. So SP k minus 1. What is the k minus 1 mean? You will pick the value from the previous list. So what is the value of I comma j in previous matrix, and what is the value of SP I comma k plus SP I comma, sorry, I comma k, k comma j.
Minimum of direct distance and one of distance.
Yeah. This is the logic for that. For the first matrix, you have to actually, sir, start from the 0. So I think sir used for in formula is k minus 1. I think k minus 1. So you have to check the direct distance and by a one node. For example, in this list, you will check from this 0 node always. For 0 to 0, so 0 to 0 is infinite, or you can say that what is the I? So all value are the I equal to 0, j equal to 0, and k is also 0. Okay, so if you put these values, so what is the distance from 0 to 0? So you can check that this is the infinite. So if you fill this value inside this, so SP, so k is 1 in this matrix. Okay, so we are finding the SP1. So k is 1, but we are putting this k minus 1. So SP I equal to 0, k minus 1 equal to 0, then plus SP k minus 1 0 and j equal to 0. So what is the minimum value? So we are comparing this infinite to this infinite. So what is the minimum of both infinite? Is infinite. So infinite is failed. Okay, infinite is failed. Same for the second. So here I equal to 0, j equal to 1, and k equal to so we are taking 1. This is also 1, but in formula we are putting the k minus 1. So same for the k. What is the value in previous matrix? So this is 10. Yeah, that means I to j direct distance is 10. If we are moving through the 0 node, okay. So if you are moving to 0 to 0, so I 0 to 0, yes, and 0 to 1. So every time we will check I to j distance and I to k, then k to j. So which is minimum, we will put that value on the next matrix. So what is the distance from I to j is 10, and what is the 0 to 0 is 0 plus, and 0 to 1 is 10. So both values 10. What is the minimum is 10. So same for fill by the here. Okay, same. So every value you have to fill by this formula SP1. Every time you will check you will put the value from the previous list. When you are creating a matrix SP1, you will pick the value from the SP0. When in the next part, when you will create the SP2 part. Okay, so here you can see the SP2 matrix. So SP2 matrix, when you create the SP2 matrix, you have to pick the value from SP1 in the formula. So we will repeat these steps 8 times. For the graph have contained the 8 nodes. So total in each matrix 8 into 8, 64 value you have to calculate, and there are 8 matrices. So you have to calculate these number of value using the given above formula. So finally you will got the SP7 matrix. Okay, SP8 matrix, yeah. So this is the matrix. Finally, you will get as a result. where it represents the shortest distance between rowth index to column index. So every pair of, for example, if you want to find out the what is the minimum distance 5 to 7. So 5 to 7, you can check that there is no path available. Infinite means there is no path available. So what is the distance between 5 to 3? So 5 to 3 is -1. Shortest distance is -1. So this is the resultant list. Actually, if nodes are more inside the graph, so manual calculation is very typical. So you have to calculate lots of value by the formula. So basically, in the practical implementation, we are performing these things because there are 3 loops: one for the matrix and second for the calculation of row and ith index value. So this is the concept of Floyd-Warshall algorithms. You have to apply this formula for calculated every cell value. So in each time you have to put the value from the previous matrix. So finally you will got the all pair shortest path value. And one question is the correctness. Okay, so where is the topic of correctness? So what is correctness? Prim solver, minimum cost is spanning tree, minimum cost is spanning tree. Okay. So correctness things. Select. So roads, spanning tree. Spanning tree, some facts of the tree. Okay. So this no. Okay. Finding strategy. Strategy. Cell outcomes. Yeah, correctness is part. Oh, lemma part. Minimum separator lemma. So for correctness, I didn't watch this lecture. Yes, explain this minimum separator lemma. I think this mathematical things are difficult. But in general, actually, we are in Correctness algorithms. Basically, we are performing. We are selecting the edge in the sorting order by the increasing order of the weights. Definitely, all small weights as will come in the graph for the spanning tree. So we are neglecting the edge which creates the cycles. So I think these mathematical things I think sir explained very well. Samit, have you cleared the algorithms, prims and coruscals? Okay, then I think I also didn't watch this lecture for the correctness minimum separator lemma. So I think you should watch once again the lectures, because this time I'm not clear for this lemma. How you sir are proving it that actually. If you have any doubt in the code part or algorithms part, you can ask. Yeah, sure. Okay, we can discuss in the next. Yeah. Okay. Any other doubts in the big 6, big 5? So there are no questions.
Sir, I have a doubt in union operation, that is in the first lecture of the week 6.
Union find
Where,
operation.
and in that, sir, how sir is getting the logarithmic answer? I'm not getting that actually.
Okay. Actually, for okay, 1 second. So yeah, so this part was still notes. So for actually big operations. Union improved implementation members. Okay. Yeah, actually in this implementation we are storing a members also, and we are also maintaining the size of the members list. So for example, if we have a graph for 0, okay. So for example, we have a h1 3 10 2 4 5 6 that, and we are starting from the creating disjoint set. So disjoint set, we will start from that. So we will create a node 0 1 2 initially 3 4 5 4 5. Okay, so this is the disjoint set. So what is the member of each nodes are only that node. So what is the size initially? What are the we are storing that component of I, member of I, and size of I. So we are storing these 3 values. So after sorting, the edge, because we will sort the edge here. So what will be the sorting sequence of edge? So first is 1, 0. Okay, so this is undirected graph, so there is one more combination will become in the adjacency list. So 1, 0, and you can say that the 0, 1. Okay, so 0, 1, then 1, 3, then next is 0, 2, then 3, 4, then 2, 5, then 4, 5, then 1, 5. Okay, so this is 1, this is 2, 3, this is 5, 6, 10. So initially all component have these values. So what one is the component value? So initially component value is C value is for 0, C value equal to 1, C value equal to 3, C value equal to 2, C value equal to 2, sorry 5, and component value equal to 4. Okay, and size of the member. So member is also same. So member is also 1, 3, and m equal to 4, m equal to 5, m equal to 2, m equal to 0. Size is also size for all is 1 initially. Size for the members length. Size is describing the members length. So s equal to 1, s equal to 1, is equal to 1. Yeah, so we will take the s from the shortest bit. So every time when we take the edge, so 0 to 1, for example, we are taking 0 to 1. So because the component of 0 and 1 are not same, so what is the component of 0 is 0. Okay, what is the component of 1 is 1. So components are not same, so we will make the union for both. That means actually we are combining this edge in the final set. After combining this, so we will store the member value. So what is the component of C0 is? So what is the actually algorithm, improved algorithm? Actually, yeah, this is the algorithm. So C old equal to component of I, we are taking the value of component of I. C new is the component of J for K in member of C old. Okay, so we will check the member of C old value. Yeah, so what is the C old is 0. Okay, component of K equal to C new, member of C new dot append C new. Okay, C new dot append K. Size of C new equal to size. Okay, so we are updating that component of K equal to C new. K of member of the 0, 0 component of 0 equal to C new. So you can apply this part, algorithm part on this diagram. So after considering this age, so we will update the member of this C0. So this become a 1. Okay. So what are the member of C new? So C new is, what is the C new? C new member of C new. So what is the C component of J? Okay, that is 1. So we will append the K value. Okay, we will append, yeah. So we will append the members list here. Yeah, this is initially this is 1, and we will append the 0 here. And what is the size of now? Now size of this is 2. So we know that we have got a component which have the size 2. After the we will consider the next edge. Okay, so Actually, this component size, it will become increase by this with this ratio, like 1, 2, 4, 8, like that. So for example, 1, 3. So next edge is 1, 3. So when we are considering this 1 and 3, so what is the component of 3 is 3, and what is the component of C1 is 1. So both are different. We will consider this edge and update the edge component. So C1.
That's right.
Okay. Code is not actually there. So what is the algorithm? Then we are once again 1 C old and 3 is new. So what is the 1 and 0? Yeah, okay. So these are the component from old. So we will append these component 1 and 0 inside this list. 3, 1, 0. Okay. And we will update the component also. So what will be the value of component? So yeah, so component of k equal to c new. C new append dot k. Okay, c new size increase component of k equal to c new. Yeah, so component of c. So it become a. So we will change this c equal to, now it become a 3. So 3, and then it is also a 3. Because for every component, so every node component value is the largest node component value will be there. Okay, so this, now the member of this C new one is 310 and size is 3. So we can maintain this member list and size for the all nodes when we considering the edge. So at any time when our size is equal to a, for example, equal to the total number of nodes in our graph, so we can break this loop also, because this size is represented that the how many nodes are connected with the tree. So this size is increasing like in that way. So initially that is one component is there, down next is 2, now next is 3. So total component is 3. So once again, if we consider the next stage, so next is 3 to 4. Okay, so 3 to 4. So log and turn this comes. Second log. Member C olds allow us to merge component I into component of J. In time C O size old. How can we make use of size C? Always merge a smaller component into larger one. Yeah. It's merge a smaller component into larger one. If size of C is less than size of C, it is. Union. Actually, we are reducing this union time to log n. Change component grows size of the components of I grows as 1 to 4. So I change component at most log n times. Size of the component of I grows. Okay, the size of the component of I. So size is increasing in that way. So, yeah. So initially component, what is the component is C0. Now it become 3. Okay, so I think confusion is also there. For each size of component, at least doubles each time after M union operation. Each union. So I think we have to write the code first, then we can explain. So this confusion is over M updates. At most 2M elements are relabeled, each one at most log n times. Log m times. So okay, so I think algorithm have some confusion also so for me. So I think in the next session I will clear all these things with the implementation part. After implementation we can clear more clear on that.
Okay, sir.
Okay. So for the next big session, I think Saturday on the this Saturday is the live coding session. So we will consider this on the next week. Okay. Anything else? Anything? Any query? Big
Actually,
six.
sir,
Hmm.
also I have in many of the codes I was implementing whenever I got logarithmic complexity I have to code in, then I face very much problem about it. Is there any solution? Because I'm getting always getting the problem about it. How to,
Complexity things.
yes, sir. How to get the logarithmic solution? It is
So logarithm solution for which implementation you are talking about?
any type means whenever we got a GRPA wherever the complexity should be logarithmic times like GRPA one of I'm getting the problems how to implement that because logarithmic solution is very difficult to think.
Yeah, so I remember that some questions related to max heap or min heap. So we know that the insert or delete operation can be performed using log n times in heap. So same for the like the binary search things, binary searching in the searching binary search tree. These are the logarithmic times. So we can find out that. So can you tell me the which question you are talking about exactly?
Week 6 GRPA ones
GRPA 1.
merging two lists.
Is there any complexity required for that? Merge K. Okay. K list. Yeah. So okay, complexity. So, okay. So log key complexity is there. That means I think some binary operation will be used for that. So you have to see, I think you should create a heap of the size k, and you can implement this. Because of that, the log term is coming for this persons. Some heap concept is involved in this person actually. So where some operation you can use the insert operation, you can use the delete operation. So it is taking some log times. Log k means some heap is created of the size k. Because of that, some log k terms is coming here.
Size k means the levels, right?
Sorry, k.
Size. You said the heaps is created of size k. Then the size k is the level. Means the levels of heap.
No, not levels. Log k. So it depends on the what operation actually are used with the heap. Actually, if size of the heap is k, then definitely insert operation will take the log k times, or delete max operation will take the log k times. Size of a heap means number of elements. So if any log term is used in the complexity for any solution, that means some operation which can be performed in the log, so you should try. So I think this week 6 related to the heap concept. So definitely some heap concept is using in this solution. So this is graded. So otherwise I cannot explain the solution. So one PPA solution I can discuss, I think. PPA 1. Okay, I think one complexity is also mentioned here. K min greater than. Okay, so here also one solution asking for the n log k times. So this log terms basically comes as one solution. Someone is provided on the discourse. This solution is available here. So in this solution, yeah, we are creating a heap. Actually, we are creating a what are the type of the heap? Yeah. So heapify min heapify. Yeah. So we are creating a min heap actually. Okay. After creating a min heap, or what are the size of the min heap is? So this is the function actually. So air of create heap for x in range k. So yeah, we are creating a log k size. Sorry, we are creating a k size of heap. We are creating a heap with k elements. So every operation we want to perform the operation insert operation, for example. So no, define create heap li. What is the okay, create heap. It will take the n times because we are creating a heap of the n complete list a and r. So what is the length of this list is n. So the size of the heap is n. After creating the min heap, we are performing the operation delete max from here, actually delete root. So this delete operation will take the log n time. So we can calculate the complexity for that. So we are performing this delete operation k times. Okay, so every time delete operation takes log n time. So for k times, so k into log n times. So this complexity of this code is k log n. So same for the graded questions. I think some heap is using in the solution, and some operation insert or deletion may be used because of that log and term is coming.
So this solution is on discourse, right?
Yeah. This solution on the discourse. Someone posted today morning.
Okay.
So same for you can use this terms, use this min heap or max heap operation in your solution code. Okay, any other query? Okay, we will repeat these topics, some implementation topics which today did not discussed. I will take on the next Thursday. Okay, if there is no query, then it shall be closed. Okay, bye everyone.
Thank you, sir.